Salam, peace be upon you. My name is Muhammad Laik Sedigi, the father of Holophase. You and I are standing at the edge of a simple question that turns out to be one of the deepest questions a language can ask. When do we say two journeys are the same? Not the same in the sense that every footstep matches, not the same in the sense that every second of travel matches, but the same in the strict sense that our language is allowed to care about inside pure Phi. Imagine you and I are walking around the lake at dawn. There are many paths. Sometimes the trail hugs the shore. Sometimes it climbs a little to avoid mud. Sometimes it dips into the trees and returns. You might stop to tie your shoe, and I might not. You might walk faster, I might walk slower. Yet if we both start at the same place, keep circling without cutting across the water, and return to the same place, there is a very strong sense in which we completed the same kind of loop, once around the lake. That phrase, once around, does not describe a drawing. It describes a class of possible drawings. That is the heart of part 21, homotopy invariance in a defect-free domain. We have already earned the pieces we need. In part 18, we learned that closure creates integers. A loop that closes in the clean domain forces a whole number claim. The sentence was, for a closed loop gamma inside the clean domain D, the integral around gamma of d phi tilde equals 2 pi times an integer n. In audio form, the loop integral of d phi tilde equals 2 pi times n, with n an integer. Discreteness, integers, arrives not because we insert it, but because a cyclic language closes. In part 19, we took that same memory and expressed it in the native circle form, holonomy. We defined the holonomy token of a loop gamma as h of gamma equals the exponential of I times the loop integral of d phi tilde. In audio, h of gamma equals exp of I times the closed-loop integral of d phi tilde. Holonomy lives in U1, the unit circle, the space of phases. It is the phase memory token a loop brings back when it returns. In part 20, we learned the grammar of combining loops. If you travel gamma 1 then gamma 2, the holonomy multiplies. In audio, h of gamma 1 composed with gamma 2 equals h of gamma 1 times h of gamma 2. Reverse the loop and you invert the token. H of gamma inverse equals h of gamma to the minus 1. This is loop composition algebra, the rule that makes global meaning computable. Now part 21 tells us something almost shocking in its simplicity. If you can smoothly deform one loop into another while staying entirely inside the clean domain D, no crossing obstructions, no leaving the domain, no sneaking across excise loci, then every topological token we have defined in pure Phi language must stay the same. Not approximately the same, exactly the same, because it is a statement about grammar, not about measurement. This is where topology becomes meaning. Let me set the intuition with a scene you can see. Picture a rubber band lying on a table. On the table, there is also a glass of water. The water is not a wall you can walk through, it is an exclusion. You can slide the rubber band around, stretch it, squash it, make it oval, make it square. You can even make it look like a rabbit's head if you're patient. But as long as you do not lift it over the glass, and as long as you do not break it, one fact remains. The rubber band is either wrapped around the glass or it is not. The exact shape does not matter. The aroundness matters. Homotopy is the formal word for this kind of change. Continuous deformation without tearing, without jumping, and, most important for us, without leaving the declared domain. And because our language is firewalled, we say this with discipline, not romance. A homotopy is not anything that feels like deformation. A homotopy is a declared process. It is a continuous family of loops, parameterized by a deformation parameter, call it S, that runs from S equals 0 to S equals 1. At S equals 0, you have loop gamma 1. At S equals 1, you have loop gamma 2. And for every intermediate S, the loop gamma of S is still a closed loop, still oriented, and still entirely inside D. If at any intermediate moment the loop touches a defect locus, crosses a boundary, or requires a cut that you did not declare, then the homotopy was not admissible. It does not count. In pure phi language, almost staying in D is the same as leaving D. One illegal instant breaks the sentence. Now we can state the invariance claim in the cleanest form. If gamma 1 and gamma 2 are homotopic inside D, then winding of gamma 1 equals winding of gamma 2, and holonomy of gamma 1 equals holonomy of gamma 2. Audio form. Homotopic in D implies same winding, same holonomy. That's the listener picture, but we also need to install why this must be true in our grammar and how the 4 gates keep it honest. Before gates, let's make the meaning land with a few examples across scales. First, human everyday reality. You've probably done this without naming it. You drive home from work. One day, you take the usual route. Another day, a road is closed, so you take a detour. You still stayed on roads. You didn't teleport. You didn't cut across private land. You didn't drive through a river. You still left the same office parking lot and returned to the same home driveway. That detour is a deformation of your route that stayed within the legal drivable domain. Your route changed shape. But the class, the fact that you went from work to home without crossing forbidden zones, stayed the same. If someone asks, "Did you go home after work?" the answer is invariant under that deformation. Second, history and behavior. Think of trade routes around the mountain range. For centuries, caravans might choose one valley or another depending on weather, safety, politics. If the mountain range is impassable, an exclusion, then route that goes around the north side and route that goes around the south side can be genuinely different classes. You can deform one route into another only if you can slide the whole path through passes that remain open. If a pass is closed or a border becomes forbidden, the domain changes and homotopy classes split. That's a topological change in the grammar of movement, not merely a change of preference. Third, biology. A metabolic cycle in a cell is not one microscopic trajectory. It is a class of trajectories. Concentrations vary. Enzyme rates fluctuate. But as long as the cycle stays within viable biochemical states, your clean domain, and returns to the same functional state, the net outcome can be invariant. Cells do not survive by requiring an exact path. They survive by requiring invariance, closure, viability, and consistency under allowed variation. Now we bring it back to pure phi. Our only allowed primitive is phi from x to s1, and the only derivative word we are allowed is a equals d phi tilde, where phi tilde is a local lift of phi to the real numbers on a lift valid patch. We already excised the domain D where these sentences are legal. On D, A is the public change word. Triunity is always present. Omega, kappa, and nu are readouts of A, never independent primitives. So whenever we talk about holonomy or winding, both built from integrating A, we are talking about global constraints on the triecho. If those global constraints change, then at least one of the readouts must be inconsistent when we recombine them back into A. In other words, homotopy invariance is also a triunity consistency law. Now we install the gates as living discipline. Gate 1, well-formedness. A homotopy statement is not a vague statement like, I can wiggle this loop into that loop. In our language, the loop gamma must be a closed loop, oriented and contained in D. And the homotopy itself must be contained in D, meaning every intermediate loop must also be a closed, oriented loop in D. So the well-formed sentence has this structure, even if we speak it in simple words. Let gamma 1 and gamma 2 be oriented closed loops in D. Suppose there exists a continuous deformation inside D from gamma 1 to gamma 2. Only then may we assert invariance of winding or holonomy. If someone forgets to mention D, the sentence is ill-typed. If someone mentions D for the endpoints, but not for the deformation, the sentence is ill-typed. In pure phi, typing is meaning. Everyday analogy. Moving furniture in a room. You can say, I moved the couch from wall A to wall B without hitting anything, only if the entire motion stayed within the free space. If at any moment the couch scraped the wall or knocked over a lamp, the claim is false. It does not matter that the start and end positions were fine. The path matters for legality. Homotopy is exactly this kind of legality statement, but for loops in D. Gate 2. Invariance. In this part, invariance means winding and holonomy depend on the homotopy class, not on the representative curve. So if gamma 1 and gamma 2 are in the same class, they must have the same invariance. And because part 20 gave us composition algebra, we also know invariance must be consistent with composition. If you deform gamma 1 into gamma 2 and you compose both with the same third loop, the results remain equivalent in token value. The grammar must not depend on how you draw or parameterize the loop, only on the class it represents. Everyday analogy, tying a knot. Two people can tie the same kind of knot with different finger motions. The knot type is the invariant. The exact path of the fingers is not. If the knot type is the same, it holds in the same essential way. The difference in finger choreography is a deformation within the legal tying domain. What matters is the class. Gate 3, domain. This is the gate most people underestimate, and it is the gate that protects us from false discoveries. Homotopy invariance holds in defect-free domains. It is not a statement about all of X. It is a statement about D, the X-size domain where the derivative language is legal. So we say it plainly. Homotopies are valid only if the entire deformation stays within D. If the loop, during deformation, crosses an X-sized boundary, or passes through a place where lift validity fails, or touches a defect locus that we have excluded, then the invariance claim does not apply, because the token was never defined there. A huge fraction of apparent violations in science and life come from a hidden domain violation. People think two paths are the same because the endpoints match, but the middle crosses a forbidden region, physically, logically, or operationally. Biology analogy, rehabilitation. A therapist moves a patient's limb from one position to another. The claim, these two positions are connected by safe motion, is only true if every intermediate angle stays inside a pain-free, damage-free range. One moment of crossing into injury range breaks the claim. That's domain-typed motion. That is homotopy with guardrails. Gate 4. Non-encodability challenge. This is where we confront the temptation to say, but I swear the exact shape matters. Sometimes it does. But in our language, if someone insists loop shape matters physically, they must prove that the dependence survives homotopy inside D and is not reducible to crossing an obstruction, changing domain type, or smuggling in an extra primitive. In other words, before we accept shape dependence as new physics, we demand a firewall audit. Are you sure your two loops are homotopic in D? Are you sure the entire deformation stays in D? Are you sure you didn't cross a hidden obstruction? Are you sure you didn't change the allowed lift, or change cuts, or implicitly change the domain? Only after that audit may shape matters be considered meaningful. This gate is not skepticism for its own sake. It is the only thing preventing the language from collapsing into storytelling. Without it, every small perturbation becomes a new effect. With it, only genuine obstructions survive as structure. Now, with gates installed, we can speak the formal prediction and falsifier in episode 13b's grammatical sense. Prediction as grammar. Holonomy and winding are stable under admissible deformations. Meaning, if gamma 1 and gamma 2 are homotopic in D, then they have identical holonomy and identical winding. Falsifier as grammar. Produce two loops that are genuinely homotopic in D, meaning you exhibit a deformation that stays in D at all times. Yet, they have different holonomy or winding, even after accounting for all permitted equivalences. Phi to phi plus c, phi tilde to phi tilde plus 2 pi n, chart change, parameterization change. If that happens, it is not an experimental anomaly. It is a failure of the token definition or a failure of our claimed invariance. Either way, the language would have to be revised. Now let's make the core idea unforgettable with a story that keeps PS0 clean. Imagine a map of an old city. The city has narrow streets, walls, and closed gates. You and I choose a loop walk. We start at the same fountain, we walk around, and we return to the fountain. The city walls are like defects. You cannot pass through them. The closed gates are like boundaries. The walkable streets are your domain D. You can deform your route. Take this alley instead of that street. Turn left earlier, linger at the market, then rejoin the road. As long as you stay in the walkable street network and never cross the walls, your aroundness relative to the walls remains. In a city with a central forbidden fortress, loops that go around it are in a different class from loops that do not. You cannot deform one into the other without crossing the fortress boundary, which is forbidden. That difference is real in the grammar. Now translate walls into pure phi, obstructions to lifting or to derivative legality. Translate street network into D. Translate loop walk into gamma. And translate memory token into holonomy H of gamma. Homotopy invariance says, if your loop walk can be deformed into mine without leaving the streets and without crossing walls, then our memory token is the same. The city can be redrawn, the route can be sketched differently, but the class is the meaning. This is why topology is not decorative. It is the minimal machinery that makes global statements possible without importing extra semantics like particle or force. It is meaning without naming. Now, we must also keep triunity alive. Holonomy is built from integrating A around the loop. A is the first derivative word. A equals d phi tilde. Omega, kappa, and nu are readouts of A: temporal cadence, spatial texture, and kinematic transport. So when we say holonomy is homotopy invariant in D, we are saying something like this. If you deform the loop without crossing an obstruction, then the accumulated A cannot change, and therefore the triaco cannot change in any way that would alter the recomposed A. If it looks like omega changed, but kappa and nu did not, that is already suspicious, because the readouts must recombine. Often what really happened is that one of the readouts was computed using a hidden change of patch, a hidden lift shift, or a hidden crossing of a cut. Homotopy invariance forces coherence among the readouts. It is a global test that your triunity bookkeeping is honest. This is why in Holophase, topology is not spatial. It is not geometry only. It is the global grammar of the change word A, and therefore the global grammar of the triaco. Now let's gather a few more analogies, because this principle shows up everywhere. In music, you can ornament a melody, add trills, change the rhythm slightly, without changing the identity of the phrase, as long as you do not cross the boundaries that define the key and cadence. Staying in key is like staying in D. Modulating to another key is like crossing an obstruction. Within the domain, the return to tonic is invariant. Different performances, same class. In social behavior, you can resolve a conflict through many conversational paths. Some are gentle, some are direct, some involve stories, some involve silence. If the conversation stays within trust, honesty, and mutual respect, your domain D, the outcome, reconciliation achieved, can be invariant across many deformations of the root. But if, at any point, the conversation crosses the defect, betrayal, humiliation, violence, the domain is broken, and you cannot claim it was the same resolution path. That is domain-typed homotopy in human life. In biology, consider animal migration routes. Birds can deviate due to wind, storms, or geography, yet still belong to the same migration corridor class as long as they remain within viable habitats and return to the same breeding grounds. If climate change destroys a corridor, introducing new defects, routes that used to be deformable into each other split into different classes. Species survival often depends on whether homotopy freedom remains available. Now we approach the closing seal of this part, and we must also bridge forward. Part 21 gives us the meaning rule. Tokens depend on classes, not drawings. But once we accept that, we immediately need the next question. What are the classes? How do we compute them? How do we classify loop types in a domain? That is why part 21 naturally points to the next installation. The idea that loop classes become the real vocabulary of the global grammar. In the roadmap you provided, part 22 is where defects are installed as phi obstructions, and later parts classify charges and linking. Those are exactly the places where class becomes computational and physical without importing semantics. But for now, we stay inside this part and give the listener one sentence to carry, plus a concise summary. Here is the carry sentence. In a defect-free domain D, if one loop can be smoothly deformed into another without ever leaving D, then every pure phi memory token, winding and holonomy, must remain exactly the same. Meaning belongs to the class, not the drawing. And now a concise summary, in plain language, with the equations spoken cleanly. Summary of part 21. We introduce homotopy in the pure phi language as continuous deformation inside the clean domain D. Two loops are homotopic in D if you can smoothly deform one into the other, while every intermediate loop stays closed, oriented, and entirely within D. Homotopy invariance then states, for such loops, winding and holonomy cannot change. Winding is the integer n from the statement the loop integral of d phi tilde equals 2 pi times n. Holonomy is the phase token. H of gamma equals exp of I times the loop integral of d phi tilde, which lives on the unit circle U1. The firewall gates keep the claim honest. The sentence must be well-formed, invariance must ignore drawings and parametrizations, the domain D must include the whole deformation, and any alleged shape dependence must pass the non-encodability challenge by showing it survives homotopy in D rather than coming from hidden obstructions. The prediction, as grammar, is stability of tokens under admissible deformation. The falsifier is two genuinely homotopic loops in D with different holonomy or winding after all allowed equivalences are accounted for. This is the moment topology becomes true meaning. The class is the word, the drawing is handwriting. And with that, we're ready to step forward into the next part, where we stop merely saying class matters and we begin to name what creates different classes. Obstructions, defects, and the integer charges they force into the language. Always peace be upon you.